than actually missed the problem. So, does anybody want to see the pyramid problem, or are we okay? Yes. Somebody got it up to give me the measurements. Somebody got the 240 was this distance, right?
The shadow was 10 meters.
Shadow was 10 meters.
And then the height was 6.2.
6.2. And we're after this, right? This height right here of that particular. I don't know, there's a, who knows how to do it that could come up and share. Come up and walk us through the.
Okay, I took the height, this is a person, right? I took
It's a
pole, okay. So I took the height of the pole, which is 6.2. And I just put it over 10 because this is 1. And then from the height of the pyramid out to the end of the shadow is 240. And we don't know what this height is. So, and then I cross multiplied. I got 148.
Anybody have questions for her? Okay.
I have a question.
Yes.
Why don't you add the shadow of the pole to the whole length of the 240?
Because the shadow of this came right out to there. So that distance is 240. So we've got this triangle right here. 240, the shadow of the pyramid was where the pole was set. And then you've got this triangle here. Are they similar? Why? What angles?
90 degree angle.
We've got the right angles.
That angle down there, that's where the sun is hitting them.
And because the sun is so far away, the rays are essentially parallel. Therefore, two parallel lines cut by a transversal, what angles? Corresponding angles are congruent. We learned in Unit 1.
Bless you.
Okay. Therefore, this little triangle is similar to this one. If it's similar, what do we know? That the sides are in the same ratio, which means they're proportional, which means we can set two ratios equal to each other. Okay? And then she said she solved it by cross multiplication. The only way I'm going to let any of you use cross multiplication to solve is if you can explain to me why it works. So who can explain that? Shannon, try it.
Okay, well, so since like 10 is equal to 240, like not equal, but they're similar. It's like they're the same unit, like
Because it's the same proportion.
But why can I go
Over 2.
6.2 times 240 is equal to 10 times x? Why can I do that? That's what cross multiplication is.
They're the same
Yeah.
ratio.
It's just kind of a shortcut. You're just not showing your work of what you're doing, because really you're just timing both sides by 240 and then both sides by 10. But then when you times 240 on this side, they cross each other out. on this side, the 10 cross each other out, so you're just not showing. your work.
Cross multiplication is a trick. It's a nice trick. It works every time. But the reason I'm bringing this up is because you're going to be dealing with students who, you'll teach them cross multiplication probably, but show them why. Let's look at this. You multiply both sides by both denominators, the product of the denominators. If we multiply both sides by 240 and 10, that's the same as that over 1, right? And the 10s cancel, right? And here the 240s cancel, leaving us with 10x and 240 times 6.2. That's why cross multiplication works, because you're essentially multiplying both sides by the product of the denominators.
So on our test, are you gonna want us to write that out, or can we cross multiply this?
If you say I cross multiply, I'd say because it's the same as multiplying both sides by the product of the denominators. You need to understand it, and your students, you need to understand it if you're going to teach it to them, because tricks alone get students into problems. Let me just tell you why. They see two fractions, and then whenever they see two fractions together, they want to cross multiply. So a problem like this: 2/3 times 3/4. They'll go, oh, that's 9 eighths or something like that. And they'll cross multiply anytime they see two fractions together, because it's just a trick. The reason this works is because the multiplication property of equality, which says if I multiply this side by a certain amount, I've got to do this side. That's why it works. Well, that and the fact that 10 over 10 is 1, which is the identity, and 1 multiplying by something doesn't change it. So this is canceled because of that, and so on. But how else could we solve that? 6.2 over 10 equals x over 240. Besides cross multiplication or multiplying both sides by the common denominator. Or by the product of the denominators, excuse me. How else could we solve this? Does anybody have any idea?
My first thought was multiplying by the reciprocal. I don't know if that works.
What do you mean?
So I cancel out one side? Or, I don't know.
So you're saying multiply both sides by 10 over 6.2?
Yeah, I don't know if that works, but that was one of my first thoughts.
Then we end up with 1 equals 10x over whatever 6.2 times 240 is. We're not getting any closer. Okay. Any other thoughts about how you might do this? Well, notice the shadow was 10. This shadow was 240. That's 24 times. So guess what? The pyramid's going to be 24 times as high as the pole. Just 6.2 times 24 is your answer. Does that make sense? If you understand proportions, there's a shortcut just thinking about it. Okay. So it's the angle shortcut that allows us to use this particular, to find the height of this pyramid. Okay.
Is that the case in the that it's angle, or the shortcut?
What do you think? We've learned 4 methods. Is it angle every time? On the mirror, this was the shadow. On the horizontal distance, and on the triangle in a triangle, Were they all angle? They were. They're not all for the same reasons. I mean, these two angles are the same because the sun's rays are parallel, and we've got we've got that the two parallel lines cut by a transversal. That's not the same reason for the mirror. The mirror one is the angle of incidence is equal to the angle of reflection. So we've got this coming in, this coming off, there's our mirror, that's equal to that because of a physics principle. Okay, but it's still, and then the person is standing here at a right angle, and the object that they're measuring is at a right angle, so there's the angle that also works. They're all angle. That's the most important one as far as application goes. Okay. Any other questions before we move on?
Bless you.
I would like to hear from someone who feels like they got pretty accurate on the archaeology plate, how they were able to determine the size of that plate. Do you want to go ahead and tell us your method? Yeah, go sideboard and draw or whatever you need to do to.
So this will be a rough sketch. But, so you have okay, that's, all these giant bricks. And so that's supposed to be the curve of the circle. And I was trying to find somewhere in here where the center of the circle is, so I could figure out the radius and the diameter that we're supposed to look for. And so what I did was I picked 2 points on the circumference or the chord of this, and then I took my compass and did find the perpendicular bisector. So when I measured it, I had made the 2 marks. It won't be exact. So I made the 2 marks with my compass and drew a straight line. And then I came up here and did the same thing. And here's my compass and made marks. Trying to guesstimate. It won't be perfect, but I made another perpendicular line. And they actually met out here on mine. But where it intersected, I figured was the center of the circle. And then I measured the radius, and they were both the same. And they were both 15.5 for the radius, which meant the diameter was twice that, which means it was 31 centimeters of drilling. That's what I did.
Okay. Anybody take a different approach? Ben?
I actually used Paint on the computer.
Okay.
I took the image and pasted it over. If you hold Control when you're making a circle or an oval when you're in Paint, if you hold Control, it'll keep the radius at all points the same. It'll make it a circle instead of an oval every time. And so I found more or less where a 90-degree angle was, so that I had a quarter of it, which I could have just used looking back at it. But I ended up just extending out a circle so that I had a full plate but only a portion of the little jagged stuff. And then I put it back into a Word document and stretched it out to the appropriate size that the original one came, so that it would be the piece that was in my Paint was the same size as the piece that came in the Word document, since it was to scale on the Word document. And then I just used the rulers on the Word document to measure it.
To measure how far across it was.
Granted, I had to convert it because the rulers are in inches and we wanted meters and centimeters.
Okay, so you used technology to draw a circle kind of superimposed on it.
Yeah.
Is that what I understood? Okay, anybody else? Abby?
I got my compass and a ruler, and I just, for my compass, it was 15 and a half. I don't know if I was able to do this, if this was against the rules. But then I...
There was no rules.
Okay, and then I put my compass on the plate, and then just like a bunch of different spots, I made a little dash, and they all made the, center. And then I put my compass on there and went around, and it went perfectly around, so.
Okay, so you set your compass to be 15.5 centimeters from the point to the pencil.
Yeah. Mm-hmm.
And then you put the point on the
Edge.
circumference, and you went out here and you said that's from there to there is 15.5,
Right.
but you didn't know exactly where.
Right.
And then you went over and tried it there, tried
Yeah.
it there, and they all started intersecting at the
crossed,
same
yeah.
place. Then you said, well, that's got to be the center. And then so she said, I'm going to assume this is a plate from the, what is this? The Greek, classical Greek plate, and go from there. And it turned out that once you did it, it fit the circle.
Yeah.
Okay. Anybody else? Serious? This is the only class I've ever taught then that didn't do it this way. I had somebody that printed this out about 5 or 6 times, copies of this. Okay, come on, talk to us.
I just printed out multiple copies and lined them up, and then took my ruler and measured it.
So do you see how she's laying them, and you can even overlap them a little bit, right? So that you know that see, you can take these, and to make sure that this is accurate, you can put this so that it overlaps a bit. Take your next one and put it, and you can actually make the entire plate, and then get your ruler out and draw the diameter. There, oh, come on! There we can look at this.
Yeah.
Hold it up.
I just stapled and then I would twist it and tweak it till I felt like it
Until
was a circle.
it looked like a circle. All right, we got some great problem solvers going on in here. Wonderful. Wonderful. Now, you just restored my confidence. I was thinking, some of you have not bought into this yet, and we're almost, we're over 2/3 the way through, about 2/3. I ask you to do things, and you go, he's never taught us to do that. I'll just bag it. No. I ask you to do things, and 3rd and 4th and 5th graders could do this kind of approach. I'm not saying find some sophisticated mathematical approach that has some formula that's out there somewhere. I'm not even saying use technology that, I'm just saying think about it and try and come up with a way. So some of you need to give just a bit more effort to it. These are all wonderful. I'll ask again, did anybody do it any different way besides what's been shown? Yeah.
I'm not sure if it was
Would be considered different or not?
because it was kind of similar to the compass one, but I just folded it, and so that the edges met with each other. I folded it in half.
Do you
and
have
I
it?
folded, no, my husband used it for physics. It's scratch paper.
Oh.
So I folded it in half so that the edges met each other, kind of like we did with the patty paper. And then I folded it again and again and found where they all intersected. All those folds intersected, so that they all curved
So-
around.
Who's got one of those pieces that... So you're saying you folded it so that when you held it up to the thing that matched,
Circles matched.
and then you creased it, and then you fold it again and creased it, and then folded it. That one is most closely related to which method that we've seen? Yeah, the one over here, which is the one I want to emphasize today. The perpendicular bisector of every chord passes through the center of the circle. No matter what circle you have. Okay? Let's illustrate that with this.